This is Brian Murray. I want to welcome you to another episode of Doc Bry, the Physics Guy. Hi everyone, and welcome to this week's blog post. These days, radioactivity has a seriously bad reputation. The problems at 3 Mile Island, Chernobyl and Fukushima demonstrate that when nuclear goes bad, it does so in a spectacular and lethal fashion. Catastrophic really doesn't do it justice. In a way, this is a real shame because now, just saying the word radioactivity is enough to make people shudder. It's not a subject people want to go near. And yet, from a physics point of view, radioactivity, its discovery and study has led to some of the most amazing leaps in our understanding of the physical universe. I thought today I would do a bit of a general post on atoms and atomic nuclei, which got me thinking about radioactivity and nuclear magnetic resonance. The first of these, radioactivity, I'm going to do a post about now. The other, NMR, I'll do a post about shortly. The great breakthroughs in radioactivity came at the turn of the last century, and one of the players of the day was Ernest Rutherford, who is considered to be one of the greatest experimentalists ever. This guy was a super heavyweight of physics and chemistry, and the periodic table, element 104, is named after him. Rutherfordium. While Rutherford was undoubtedly one of the great contributors to the study of radioactivity, I think that the most famous person associated with radioactivity must be Marie Curie, Nobel Prize winner in both physics and chemistry, the only person to win 2 prizes in the sciences. Curie discovered polonium and radium. These elements provided Rutherford with the materials he needed to do his great work. She came up with the name radioactivity. She was also instrumental in developing the use of X-rays in medicine. The Red Cross actually made her head of its radiology service. Today, there are numerous schools and institutes that bear her name. Her research and long-term exposure to radioactive substances would eventually cause her to get cancer that would ultimately kill her. Cancer research and cancer charities now carry her name. Albert Einstein once remarked that Marie Curie was probably the only person not corrupted by fame. What a superstar. Marie Curie, I think you're great. In Liverpool, where I'm from, they planted 1 million daffodils in Sefton Park in her honour. It's called the Field of Hope, and when it's in bloom, it's a sight to behold. If ever you get a chance to go to Liverpool when the daffodils are out, it's amazing. It really is. It's just fantastic. I also think radioactivity is great because it features the nucleus of the atom, that magnificent tiny speck at the centre of all atoms. Apart from hydrogen, which is a bit of a special case in many ways, all nuclei consist of combinations of protons and neutrons. It's the protons in the nucleus which determine what elements we're dealing with. For example, any atom with 6 protons is a nucleus of carbon. If it's got 7 protons, it won't be carbon, it'll be nitrogen. Carbon typically has 6 protons and 6 neutrons, but it can have 8, and this is carbon-14. Nitrogen usually has 7 protons and 7 neutrons, so it's nitrogen-14. Now, nitrogen-14 is very similar in mass to carbon-14, but it's completely different because of the 1 proton, and this changes everything and gives us the 2 very distinct elements. There are no 2 elements with the same amount of protons, though there are some with the same amount of neutrons, or with the same total number of protons and neutrons. Isotopes are variants within a single element, and by this we mean that an element can have atoms with different number of neutrons, just like carbon-12, carbon-13 and carbon-14. These are all isotopes of carbon. Some isotopes are found to be unstable and are known to be radioactive. They can undergo a reaction resulting in a particle being ejected from the nucleus. The most common types of radiation are alpha, beta and gamma radiation. There's certainly more than this though, including a proton emission and neutron emission, as well as positron emission, but we'll come back to that one later. The names alpha, beta and gamma are from the Greek alphabet and were used by Rutherford and another guy called Villard to describe the different types of radiation that they had witnessed in experiments. At the time, they had no idea what they actually were. It took Rutherford 7 years to prove that alpha particles were actually the same as the helium nucleus. The beta particle was known to be far more penetrating than the alpha particle, but again it took a considerable time to prove that it was in fact an electron. The realisation that a beta particle was an electron was a major discovery because it showed that electrons can originate from the nucleus, even though we know that the nucleus only contains neutrons and protons. This in turn led to the idea that a neutron can decay into a proton and an electron, and it's the electron that's then ejected as a beta particle. Imagine having the brains and the imagination to figure that one out. I mean, that's just massive. It was Villard who discovered gamma rays while studying radium in 1900, and it was Rutherford who gave it its name in 1903. Thing is, these are not particles, they're just high energy light waves. They're so energetic that they can go through a fair amount of lead shielding. The discovery of radioactivity and its associated properties led to a rather astonishing idea, and it was this: it should be possible to use this behaviour to calculate just how old the Earth is. The idea was dreamed up by Rutherford, who you may have gathered was a bit of a bright chap, and this was in 1905, the same year Einstein was publishing his ideas on special relativity. Rutherford realised, you see, that radioactivity was due to some atoms changing into lighter elements and emitting alpha, beta or gamma radiation. He also discovered that particular isotopes of a specific element decay at distinctive rates, and this is now called the half-life. Imagine you had 1 billion atoms of uranium-235. The half-life is the time it takes for 500 million of them to decay into something else. It turns out that uranium and thorium have very long half-lives, and so they stay for long periods, which is why they're so difficult to manage when we take them out of nuclear reactors. They stay radioactive pretty much forever. Rutherford figured that it might be possible to work out the age of the Earth from the relative proportions of radioactive materials in rock samples. Now this is slightly trickier than you might think, because some of the particles that they produce are also radioactive. So you end up with a sort of family decay tree with radioactive parents, radioactive children and radioactive grandchildren, and so on. In the following 50 years since this idea was first put forward by Rutherford, it was investigated and refined. There's now about 40 different techniques that are being used, working with a fairly large variety of radioactive materials. The result is that the Earth is about 4.5 billion years old, which is only about 1/3 the age of the known universe, but it's similar to the age of the Sun. It's now thought that it formed within about 100 million years after the Sun fired up. 100 million years. I mean, we can pop it into a sentence as if it's nothing, but think about that for 1 minute. 100 million years after the Sun fired up, we think the Earth formed. The Earth has been here for 4.5 billion years. This is a period of time that is just so far beyond our imagination. Atoms on Earth have been undergoing radioactive decay for that entire period, the 4.5 billion years. This is loads of atoms undergoing loads of decay, and it's still going on. We still have radioactive elements in the Earth. For all that time, this process has been going on and on and on. Just imagine how many atoms have undergone decay in that time, and yet there's still loads left. It's thought that it's radioactivity in the Earth's crust and mantle that helps heat the Earth from the inside. In recent times, thorium has started to be promoted as a potentially safe radioactive source for use in nuclear reactors, but I'll do a post on that one another day. There's no doubt that the story of radioactivity is not over, and this century may yet deliver its finest hour. And who knows, maybe it'll be you who helps to do that. This is Dr. Bry, the physics guy. Hey everyone, this is Dr. Bry, the physics guy. I hope you enjoyed this episode. If you did, can you share it with your friends, your fellow students, and anyone you think might be interested? That'd be great, and you'd be doing me a massive favour. Subscribe now so that you don't miss out on the latest episodes and news. And check out my website right now at drbry.com. That's drbry.com. And for a limited time, I'm giving away the first part of my 7 ingredients course. It's absolutely free. There's almost 40 minutes of free video explaining the course and why you have what it takes to do physics and how it can change your life forever. And there's also a free download that you can keep. All the details are on my website. I'm also on YouTube, Instagram and Facebook, and all the details are there on drbry.com, drbry.com. I look forward to seeing you soon.